Welcome to a journey through the cosmos, where mysteries drift between the stars and find their way to us. Tonight, we're going to explore something that shouldn't exist, yet does. Something that arrived unannounced, challenged everything we thought we knew, and then vanished into the darkness as mysteriously as it came. Let the worries of your day dissolve. Forget about time. Forget about tomorrow's responsibilities. For the next while, there's only you, the vast emptiness of space, and a visitor that came from somewhere so distant that light itself takes decades to make the journey. Close your eyes if you wish, let your mind drift, and prepare to encounter Oumuamua. In October 2017, a Canadian astronomer named Robert Warwick was doing what astronomers do best, staring into the void, waiting for something extraordinary to happen. He was using the Pan-STARRS 1 telescope, perched on the volcanic slopes of Haleakala in Hawaii, when he noticed something that shouldn't have been there, a point of light moving too fast, in the wrong direction, behaving like nothing he'd ever seen before. The object was traveling at 196,000 miles per hour through our solar system. To put that in perspective, that's fast enough to cross the United States in about 2 minutes. But speed wasn't the strange part. What made this discovery remarkable was that this visitor wasn't bound by our sun's gravity. It was passing through, like a cosmic wanderer with somewhere else to be. Oumuamua had already made its closest approach to the sun 6 weeks before anyone noticed it. On September 9th, 2017, it had swooped within 24 million miles of our star, closer than Mercury's orbit, absorbing solar energy and beginning its long journey back to the interstellar void. By the time Warwick spotted it, the object was already 21 million miles from Earth, receding rapidly into the darkness. The name Oumuamua comes from Hawaiian, chosen by the Pan-STARRS team in consultation with language experts at the University of Hawaii. It means a messenger from afar arriving first, though some translations suggest scout or reach out for first. The word begins with an okina, not an apostrophe, representing a glottal stop in Hawaiian pronunciation. It's a fitting name for humanity's first confirmed visitor from another star system. When astronomers calculated Oumuamua's trajectory, they discovered something that sent ripples through the scientific community. The object had an orbital eccentricity of 1.20, meaning it was traveling on a hyperbolic path. Anything with an eccentricity greater than 1.0 exceeds the sun's escape velocity and cannot be gravitationally bound to our solar system. This wasn't a comet or asteroid that had wandered in from the outer reaches of our cosmic neighborhood. This was genuinely alien. The Discovery team worked backwards through Oumuamua's path and found that it had entered our solar system from the direction of the constellation Lyra, roughly where the bright star Vega sits in our night sky. But here's where the story gets interesting. Even though Oumuamua seemed to come from Vega's direction, it didn't actually originate there. The object had been traveling through space for so long that when it passed near Vega 300,000 years ago, that star was in a completely different position. Initially classified as an asteroid and given the designation 2017 U1, Oumuamua was quickly reclassified as a comet when astronomers realized its unusual behavior. But it didn't behave like any comet they'd ever seen. Where was the coma, the glowing envelope of gas and dust that forms when comets approach the sun? Where was the characteristic tail streaming away from the solar wind? Oumuamua showed no signs of outgassing whatsoever. No tail, no coma, no visible ejection of material. It appeared completely inert, like a dark piece of space rock tumbling through the void. Yet as telescopes tracked its departure from the solar system, they detected something puzzling. The object was accelerating slightly faster than it should have been under the influence of gravity alone. This subtle acceleration was the kind typically seen in comets, caused by jets of gas streaming from their surface as they warm up near the sun. But Oumuamua showed no visual evidence of such outgassing. The acceleration was real, measured by multiple instruments, including the Hubble Space Telescope, but the cause remained mysteriously invisible. The object's shape was perhaps its most bizarre characteristic. As Oumuamua tumbled through space, its brightness changed dramatically, varying by a factor of 10 every 7.3 hours. This suggested an extremely elongated object, unlike anything previously observed in our solar system. Initial estimates suggested it was shaped like a cigar, roughly 10 times longer than it was wide. No known asteroid or comet from our solar system displays such extreme proportions. The most elongated objects previously observed were no more than 3 times longer than their width. Oumuamua was apparently up to 1,300 feet long and only about 130 feet wide, though these dimensions were inferred from its light curve rather than direct observation. The object's color provided another clue to its nature. Spectroscopic analysis revealed that Oumuamua had a reddish hue, similar to objects in the outer regions of our solar system. This reddening is typically caused by long exposure to cosmic radiation, which breaks down organic compounds on the surface into complex molecules called tholins. The red coloration suggested that Oumuamua had been wandering through interstellar space for hundreds of millions of years. Given its small size and faintness, Oumuamua presented an enormous challenge for astronomers. The object was only about as bright as a 20th magnitude star, requiring large telescopes to detect. As it raced away from the sun, it grew dimmer by the day. By the end of October 2017, just weeks after its discovery, it had faded to 23rd magnitude. By December, it was too faint and fast-moving for even the world's largest telescopes to track. The limited observation window created a sense of urgency unlike anything the astronomical community had experienced before. Telescopes around the world were rapidly redirected to capture as much data as possible before Oumuamua vanished forever. The European Southern Observatory's Very Large Telescope in Chile, the Gemini South Telescope, the Keck 2 telescope in Hawaii, and NASA's space-based Hubble and Spitzer telescopes all joined the effort. During the brief weeks of observation, astronomers gathered enough data to determine that Oumuamua was tumbling in an unusual way. Rather than spinning around a single axis like a typical asteroid, it appeared to be tumbling end over end, like a bottle rolling across the ground. This complex rotation pattern made determining its exact shape even more challenging. The density of Oumuamua remained a mystery. If it were a loose collection of rocks and ice, similar to many comets, it would need to have a density comparable to rocky asteroids to maintain its structural integrity while tumbling. If it had even a small amount of internal strength, like an icy comet, it could maintain a much lower density without flying apart. As Oumuamua departed our solar system, its trajectory took it about 20 degrees above the plane where most planets orbit the Sun. It passed beyond Mars's orbit in November 2017, would cross Jupiter's orbital path in May 2018, and move beyond Saturn's orbit in January 2019. Eventually, it would head toward the constellation Pegasus, carrying with it more questions than answers. The discovery of Oumuamua confirmed what astronomers had long predicted, that interstellar space is filled with wandering objects ejected from their home star systems. Computer models suggested that such objects should be common, with perhaps one passing through the inner solar system every year. The fact that we had never seen one before was simply because our telescopes weren't sensitive enough to detect such small, dark, fast-moving objects. Survey telescopes like Pan-STARRS 1 represent a new generation of skywatching instruments powerful enough to spot these cosmic nomads. As these systems improve and more come online, astronomers expect to discover many more interstellar visitors. Each one will provide a unique window into the formation and evolution of planetary systems beyond our own. The scientific community began proposing theories to explain Oumuamua's unusual properties almost immediately. Some suggested it might be a piece of a larger body that had been shattered by a collision or torn apart by tidal forces. Others proposed it could be the remnant of a disintegrated comet that had lost most of its volatile materials during its long journey through interstellar space. One of the more exotic theories suggested that Oumuamua might be composed of hydrogen ice. In the cold depths of interstellar space, hydrogen could theoretically freeze into solid form. Such an object would be nearly transparent and would sublimate as it approached the sun, creating thrust without producing a visible coma. However, critics pointed out that hydrogen ice would be extremely fragile and unlikely to survive the stresses of interstellar travel. Another hypothesis proposed that Oumuamua might be a fragment of a Pluto-like world, rich in nitrogen ice. Computer models showed that such an object could survive in interstellar space for hundreds of millions of years and would sublimate nitrogen gas when heated by the sun. The expelled nitrogen would be invisible to ground-based telescopes, but could account for the observed acceleration. The possibility that Oumuamua might be artificially manufactured generated considerable public interest and scientific debate. Harvard astronomer Avi Loeb became a prominent advocate for this hypothesis, arguing that the object's unusual properties were consistent with a light sail or other form of alien technology. He pointed to its extreme shape, its acceleration pattern, and the lack of visible outgassing as potential evidence of artificial origin. Most astronomers, however, remained skeptical of the artificial hypothesis. They argued that natural explanations, while exotic, were more plausible than invoking extraterrestrial technology. The scientific principle of Occam's razor suggests that the simplest explanation consistent with the evidence is usually correct, and several natural mechanisms could potentially account for Oumuamua's behavior. Radio telescopes, including the Green Bank Telescope in West Virginia, were directed toward Oumuamua to search for any artificial signals that might indicate technological origin. The observations conducted as part of the Breakthrough Listen project detected no radio emissions from the object across multiple frequency bands. While this didn't definitively rule out artificial origin, it failed to provide the evidence that would support such an extraordinary claim. The Spitzer Space Telescope, which observes in infrared wavelengths, also studied Oumuamua, but was unable to detect any thermal emission from the object. This non-detection placed constraints on the object's size and suggested it was smaller than initially estimated, perhaps only 300 to 400 meters in length, rather than the kilometer-plus dimensions suggested by early observations. As more data accumulated, the scientific community began to converge on explanations involving outgassing of materials invisible to optical telescopes. The 2023 study by Jennifer Bergner and Daryl Seligman proposed that Oumuamua could be explained as a water-rich comet that had been processed by cosmic radiation during its interstellar journey. According to their model, high-energy cosmic rays pervading the galaxy could convert up to 30% of the water ice in a comet into molecular hydrogen. This hydrogen would become trapped within the remaining ice structure. As Oumuamua approached the sun and warmed up, the trapped hydrogen would be released, providing the thrust observed by astronomers without creating a visible tail. The hydrogen outgassing hypothesis elegantly explained several of Oumuamua's puzzling characteristics. Molecular hydrogen is much lighter than the carbon dioxide and water vapor typically ejected by comets, so it wouldn't have enough momentum to drag dust particles along with it. This would explain why no coma or tail was visible. The process would also occur over the entire surface of the object, rather than from specific jets, explaining the relatively smooth acceleration profile. This theory also suggested that Oumuamua was not as exotic as initially thought. Rather than being a unique cosmic oddity, it might be representative of a common class of objects, interstellar comets that have been aged and processed by their long journey through space. Every comet ejected from a star system would undergo similar processing, creating a population of hydrogen outgassing objects in interstellar space. The discovery of a second interstellar object in 2019 provided an interesting comparison. 2I/Borisov, discovered by amateur astronomer Gennady Borisov using a homemade telescope in Crimea, behaved much more like astronomers expected an interstellar comet to behave. It displayed a clear coma and tail, showed typical cometary spectral features, and followed predictable outgassing patterns as it approached the sun. The contrast between Oumuamua and Borisov highlighted the diversity that likely exists among interstellar objects. While Borisov appeared to be a relatively fresh comet that had retained most of its volatile materials, Oumuamua might represent the other end of the spectrum, an ancient wanderer that had been thoroughly processed by its long journey between the stars. Estimates suggest that there could be thousands of Oumuamua-sized objects within Neptune's orbit at any given time, invisible to our telescopes until they pass close to the Sun and reflect enough sunlight to be detected. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, is expected to dramatically increase the rate of interstellar object discoveries with its wide field of view and sensitive detectors. The brief visit of Oumuamua raised questions about our preparedness for studying such objects. By the time its interstellar origin was confirmed, it was already racing away from the Sun and growing dimmer by the day. Future discoveries will benefit from improved automated detection systems that can identify unusual objects more quickly, allowing for more detailed study while they remain bright enough to observe. Several research groups have proposed ambitious missions to intercept Oumuamua using gravity assist maneuvers around Jupiter and other planets. These mission concepts would require decades to reach the object, but they could provide the close-up observations needed to definitively determine its nature and composition. However, the technical challenges and costs of such missions make them unlikely to be approved in the near term. A more practical approach involves preparing for the next interstellar visitor. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, is designed to rendezvous with a pristine comet or potentially an interstellar object. The spacecraft will wait at a gravitationally stable point in space until a suitable target is identified, then rapidly maneuver to intercept it. The study of Oumuamua has implications beyond our understanding of interstellar objects. These wandering bodies serve as messengers from other star systems, carrying information about the processes of planetary formation and evolution throughout the galaxy. Their compositions can tell us about the environments in which they formed, while their trajectories provide clues about the gravitational dynamics that ejected them from their home systems. Computer simulations suggest that most interstellar objects are ejected during the early stages of planetary system formation, when massive planets migrate inward and gravitationally scatter smaller bodies. This process may be common throughout the galaxy, implying that every star system contributes to a vast population of wandering objects in interstellar space. The fact that we detected Oumuamua at all suggests that such objects are more common than previously estimated. Early predictions, based on theoretical models, suggested that interstellar objects might pass through the inner solar system once every few thousand years. The discovery of 2 objects in just 2 years implies they may be orders of magnitude more abundant than those models predicted. This abundance has profound implications for our understanding of planetary system formation. If interstellar objects are as common as recent observations suggest, then the process of planetary formation must be incredibly wasteful, ejecting far more material than it retains. Our own solar system likely contributed to this cosmic debris field during its early evolution, scattering countless objects into interstellar space. The chemical composition of interstellar objects could provide insights into the diversity of planetary systems throughout the galaxy. Objects formed in systems with different stellar metallicities, different disk masses, or different planetary architectures would be expected to have distinct compositional signatures. A large sample of well-characterized interstellar objects could effectively serve as a survey of galactic planetary systems. Oumuamua's journey through our solar system was remarkably brief. From discovery to disappearance, telescopes had only about 3 months to study it. During this time, it traveled from beyond Mars's orbit to a point where it was too faint to observe, covering a distance of hundreds of millions of miles. The object provided a tantalizing glimpse of the broader population of interstellar wanderers that surround us. The rotational properties of Oumuamua suggested a complex history, Its tumbling motion indicated that it was not in a state of minimal energy rotation, which would be expected for an object that had been spinning freely for millions of years. This non-principal axis rotation could have been induced by outgassing torques, collisions with other objects, or tidal forces encountered during its interstellar journey. The surface temperature of Oumuamua varied dramatically as it tumbled through space. When its long axis pointed toward the sun, it would absorb maximum solar radiation and heat up significantly. When presenting its narrower profile, it would cool down. This thermal cycling could have driven sublimation of trapped gases, contributing to the observed acceleration and complex rotational state. Spectroscopic observations of Oumuamua were limited by its faintness and rapid motion, but they revealed a relatively featureless spectrum typical of space-weathered surfaces. The lack of absorption features associated with water ice, carbon dioxide, or other common cometary materials was initially puzzling, but is now understood to be consistent with a surface that has been heavily processed by cosmic radiation and micrometeorite bombardment. The discovery of Oumuamua marked the beginning of a new field of astronomy, the study of interstellar objects within our solar system. These cosmic visitors provide a unique opportunity to study material from other star systems without the need for interstellar travel. Each object carries with it a record of the conditions in its formation environment and the processes it has experienced during its journey through space. The public fascination with Oumuamua reflected humanity's deep curiosity about our place in the universe. Here was tangible evidence that our solar system is not isolated, but part of a vast cosmic ecosystem where material regularly travels between star systems. The object served as a reminder that space is not empty, but filled with wandering remnants of planetary formation from throughout the galaxy. Media coverage of Oumuamua often focused on the possibility of artificial origin, though this remained a minority view among scientists. The extraterrestrial hypothesis captured public imagination precisely because it suggested that we might not be alone in the universe. While no evidence supported this interpretation, the possibility that advanced civilizations might use the interstellar medium to transport technology cannot be entirely dismissed. The shapes proposed for Oumuamua ranged from the initial cigar-like model to more exotic pancake or disc configurations. Some researchers suggested it might be extremely flat, like a cosmic cookie or pancake, rather than elongated like a cigar. Both shapes could produce similar light curves, making it impossible to distinguish between them based solely on brightness variations. Computer models of Oumuamua's structure suggested that if it were indeed as elongated as its light curve implied, it would need to be a relatively solid object to avoid breaking apart under rotational stress. A loose rubble pile with such extreme proportions would likely fly apart due to centrifugal forces. This structural requirement placed constraints on its composition and formation mechanism. The metallic content of Oumuamua remained uncertain, though its density and lack of observable outgassing suggested it might contain significant amounts of rock and metal. Some models proposed that it could be almost entirely metallic, perhaps the core of a larger body that had been stripped of its rocky and icy outer layers by some violent process. Alternative formation scenarios for Oumuamua included tidal disruption of a larger body during a close encounter with a massive object, impact fragmentation from a collision between asteroids or comets. Alternative formation scenarios for Oumuamua included tidal disruption of a larger body during a close encounter with a massive object, impact fragmentation from a collision between asteroids or comets, or erosion of a larger object during its passage through dense interstellar medium. Each of these processes could potentially produce objects with unusual shapes and compositions. The lack of detectable water vapor or other common cometary gases from Oumuamua initially led astronomers to classify it as an asteroid rather than a comet. However, the detection of non-gravitational acceleration forced a reclassification, as asteroids do not typically experience such forces. This highlighted the limitations of traditional classification schemes when applied to objects from other star systems. The trajectory of Oumuamua provided clues about its origin and history. Its incoming velocity relative to the local standard of rest was typical of stars in the solar neighborhood, suggesting it had not traveled an enormous distance or been accelerated by unusual processes. The object appeared to be a typical representative of the local interstellar population, rather than an exotic visitor from the galactic core or halo. Attempts to trace Oumuamua's path backward through the galaxy identified several potential source regions, but none could be definitively confirmed as its origin. The gravitational influence of the Milky Way's spiral arms and other massive structures makes it extremely difficult to determine where an object was located millions of years ago. Oumuamua could have originated from any of thousands of star systems within a few hundred light years of the Sun. The age of Oumuamua's surface, inferred from its red color and spectroscopic properties, suggested it had been exposed to the interstellar medium environment for hundreds of millions of years. This implies either a very long journey from a distant star system or ejection from a relatively nearby system in the distant past. Either possibility highlights the vast timescales involved in interstellar transport. The discovery paper describing Oumuamua was published in the journal Nature in November 2017, just 1 month after the object's discovery. This rapid publication reflected the urgency felt by the astronomical community to share their findings before the object disappeared beyond the reach of telescopes. The paper has since become one of the most cited astronomy papers of the decade. Follow-up studies of Oumuamua continued long after the object itself had faded from view. Researchers reanalyzed the available data using improved techniques, developed new theoretical models to explain its properties, and used the observations to constrain models of interstellar object populations. These efforts have continued to refine our understanding of what Oumuamua was and what it represented. The amateur astronomy community played a crucial role in observing Oumuamua during its brief passage through the solar system. Advanced amateur telescopes and CCD cameras allowed dedicated observers to contribute meaningful photometric data, helping to characterize the object's rotation period and shape. This collaboration between professional and amateur astronomers exemplified the democratization of astronomical research. The infrared observations of Oumuamua by the Spitzer Space Telescope provided important constraints on its size and thermal properties. The lack of detectable thermal emission implied that the object was smaller and less active than initially estimated. These observations also ruled out significant outgassing of dust particles, which would have created a detectable infrared signature. Attempts to model Oumuamua's internal structure suggested that it might be differentiated with denser materials concentrated toward its center and lighter materials on the surface. Such differentiation could result from partial melting during its formation or from impact processing that preferentially removed lighter surface materials while leaving behind a denser core. The discovery of Oumuamua validated decades of theoretical work predicting the existence of interstellar objects. Models of planetary system formation had long suggested that such objects should be common, but detecting them required telescopes sensitive enough to spot small, dark objects moving rapidly across the sky. The success of Pan-STARRS 1 in making this discovery demonstrated the power of modern survey telescopes. The international collaboration that characterized Oumuamua research demonstrated the global nature of modern astronomy. Telescopes in Hawaii, Chile, the Canary Islands, and space-based observatories all contributed observations, while researchers from dozens of countries collaborated on analysis and interpretation. This worldwide effort maximized the scientific return from the brief observation window. The naming process for Oumuamua reflected the Hawaiian culture's deep connection to navigation and exploration. Ancient Polynesian navigators used careful observation of stars, currents, and wildlife to traverse vast oceanic distances, making them some of history's most accomplished explorers. The choice of a Hawaiian name for our first confirmed interstellar visitor honored this tradition of discovery and exploration. The detection of Oumuamua required sophisticated automated systems capable of identifying unusual objects among the millions of stars and galaxies recorded each night by survey telescopes. The Pan-STARRS Moving Object Processing System uses complex algorithms to identify objects that move between sequential images, then calculate their orbits to determine which ones might be of interest to astronomers. The brief lifetime of Oumuamua in our observational window highlighted the need for rapid response capabilities in astronomy. Future surveys will need to quickly identify potentially interesting objects and immediately alert the global astronomy community to maximize observation time. Machine learning and artificial intelligence are increasingly being used to automate these processes. The study of Oumuamua revealed the importance of archival astronomy data. Researchers searched through previous sky survey images to see if the object had been captured before its official discovery, potentially extending the observation baseline. While no clear pre-discovery images were found, this effort demonstrated how astronomical archives can provide valuable additional data for unusual objects. The economic impact of Oumuamua research was substantial, though difficult to quantify precisely. Telescope time is extremely valuable, and the decision to redirect major observatories to study this single object represented an investment of millions of dollars in opportunity cost. The scientific return, however, was considered invaluable for advancing our understanding of the cosmos. Educational institutions around the world incorporated Oumuamua into their curricula as an example of cutting-edge astronomical research. The object's mysterious properties and potential implications for astrobiology made it an ideal case study for engaging students in scientific thinking and the process of hypothesis testing. The legacy of Oumuamua extends beyond its specific scientific contributions to its role in preparing the astronomical community for future interstellar visitors. The lessons learned from studying this object have informed plans for next-generation telescopes and rapid response systems that will be better equipped to characterize future interstellar objects. Computer simulations of the galactic population of interstellar objects suggest that Oumuamua-like bodies may be among the most common types of objects in interstellar space. If confirmed by future observations, this would imply that the process of planetary formation is remarkably inefficient, ejecting far more material than it retains around parent stars. The possibility that Oumuamua originated from a disrupted exoplanet adds an intriguing dimension to exoplanet research. If pieces of exoplanets regularly visit our solar system, they could provide direct samples of worlds orbiting distant stars. Advanced analytical techniques might eventually allow us to determine not just the composition of these fragments, but potentially even whether they originated from planets that could have supported life. The unusual acceleration of Oumuamua, while ultimately explained by natural processes, served as a reminder that the universe still holds many surprises. The initial inability to explain this acceleration using conventional models highlighted the importance of remaining open to unexpected discoveries and exotic explanations when dealing with unprecedented observations. The three-dimensional trajectory of Oumuamua through the solar system was complex, influenced by the gravitational fields of the Sun and major planets. Computer models tracked its path with extraordinary precision, accounting for relativistic effects and non-gravitational forces. These calculations were essential for understanding where the object came from and where it was going. The public response to Oumuamua demonstrated both the widespread fascination with space exploration and the challenge of communicating scientific uncertainty to general audiences. Media coverage often focused on the most speculative explanations while underplaying the more mundane but likely natural origins. This highlighted the ongoing need for clear scientific communication about cutting-edge research. The discovery of Oumuamua occurred during a period of rapid advancement in astronomical instrumentation and techniques. The combination of sensitive CCD detectors, fast computers for data processing, and sophisticated software for orbit determination made it possible to quickly identify and characterize this unusual object. Earlier generations of telescopes might have missed it entirely or been unable to determine its interstellar origin. The long-term scientific value of Oumuamua research will likely come from its role as the first member of a new class of objects rather than from any unique properties it possessed. As more interstellar objects are discovered and characterized, Oumuamua will serve as the baseline against which others are compared, helping astronomers understand the diversity and common properties of these cosmic wanderers. Current estimates suggest that approximately one interstellar object like Oumuamua passes through the inner solar system each year, though most remain undetected due to their small size and high speed. The Vera C. Rubin Observatory, with its large mirror and wide field of view, is expected to discover dozens or even hundreds of such objects annually once it begins operations. The study of Oumuamua contributions to astrobiology by demonstrating that material regularly travels between star systems. While this particular object showed no signs of biological origin, the possibility that microorganisms could survive the journey between stars on such objects has implications for theories about the spread of life throughout the galaxy. The rotation state of Oumuamua provided insights into the violence of its ejection from its parent system or its experiences during interstellar travel. The complex tumbling motion suggested that the object had experienced significant torques, either from outgassing or from close encounters with other bodies. Understanding these processes helps astronomers interpret similar behavior in future interstellar visitors. The apparent lack of impact craters on Oumuamua, inferred from its smooth light curve, suggested either a very young surface or a composition resistant to cratering. In the context of its likely ancient age, this implied ongoing surface modification processes, possibly including sublimation, thermal cycling, or space weathering that continuously erased impact features. The discovery of Oumuamua marked a transition point in astronomy from the theoretical prediction of interstellar objects to their regular observation and study. This transition parallels earlier developments in astronomy, such as the progression from predicted to observed exoplanets, demonstrating how technological advances continue to open new windows on the universe. And so Oumuamua continues its journey into the cosmic night, carrying with it the secrets of its origin and the memories of its brief encounter with our civilization. By now, it has passed beyond the orbit of Neptune, growing ever dimmer and more distant until it becomes once again just another invisible wanderer in the vast darkness between the stars. In a few thousand years, Oumuamua will pass beyond the gravitational influence of our sun entirely, becoming truly interstellar once more. It will drift for millions of years through the void, perhaps eventually encountering another star system where it might again briefly shine in the light of an alien sun, observed perhaps by other minds, wondering about its nature and origin. The story of Oumuamua reminds us that our solar system is not an isolated island in space, but part of a vast cosmic ocean where countless objects drift between the stars, carrying tales of worlds beyond imagination. In its brief visit, this mysterious messenger showed us that the universe is stranger and more connected than we ever imagined, and that sometimes the most profound discoveries come from things that arrive unannounced and challenge everything we thought we knew. As you drift toward sleep, let your mind wander with Oumuamua through the cosmic dark, past worlds unimaginable, through clouds of ancient starlight, toward whatever distant destination awaits in the infinite depths of space. In the silence between heartbeats, in the pause between thoughts, there is a universe of wonder waiting to be discovered, where mysterious messengers carry secrets between the stars, and every point of light in the night sky marks a destination we have yet to explore. The cosmos is vast and full of mysteries. Oumuamua was just the beginning. The technological achievement required to detect Oumuamua cannot be understated. The Pan-STARRS 1 telescope that first spotted this cosmic wanderer represents the culmination of decades of advancement in astronomical instrumentation. Its 1.8-meter mirror may seem modest compared to larger telescopes, but its wide field of view and sensitive digital detectors make it uniquely suited for discovering fast-moving objects in the solar system. The camera system on Pan-STARRS 1 consists of an array of 60 charge-coupled devices, each containing over 4 million pixels. This creates a mosaic capable of recording an area of sky equivalent to 36 full moons in a single exposure. Every clear night, the telescope systematically scans the entire visible sky, generating terabytes of data that must be processed and analyzed for potentially interesting objects. The software systems that identify moving objects like Oumuamua are marvels of modern computing. They must distinguish between genuine solar system objects and instrumental artifacts, cosmic ray hits, satellite trails, and other sources of false alarms. The algorithms compare images taken minutes apart, looking for objects that have moved against the background of stars. This sounds simple in principle, but the implementation requires sophisticated mathematical techniques to handle the distortions caused by Earth's atmosphere and the telescope's optical system. When Oumuamua was first detected, it appeared as nothing more than a faint point of light that had shifted position between consecutive images. The initial observations suggested it might be an ordinary asteroid, though its orbit seemed unusual. Only after several nights of follow-up observations did astronomers realize they were looking at something extraordinary. The process of confirming Oumuamua's interstellar origin required precise measurements of its position over time. Even tiny errors in these measurements could completely change the calculated orbit. The work demanded coordination between multiple observatories, each contributing their own positional measurements to refine the trajectory calculation. The margin for error was vanishingly small when dealing with an object moving at such tremendous speed. The gravitational environment that Oumuamua navigated during its passage through the solar system is incredibly complex. While the Sun's gravity dominates, the gravitational influences of Jupiter, Saturn, and the other planets create subtle perturbations that must be accounted for in any precise orbital calculation. Even the relatively tiny gravitational pull of asteroids like Ceres can have measurable effects on the trajectory of a small, fast-moving object. During its closest approach to the Sun, Oumuamua experienced temperatures that would have caused significant thermal stress in any normal rocky body. The temperature difference between its sunlit and shadowed sides could have reached hundreds of degrees, causing expansion and contraction that might fracture a brittle object. The fact that it maintained its structural integrity through this thermal cycling provides clues about its composition and internal structure. The magnetic field environment through which Oumuamua passed also deserves consideration. The solar wind, a stream of charged particles flowing outward from the Sun, creates a complex magnetic field structure throughout the solar system. While Oumuamua showed no signs of having its own magnetic field or of interacting strongly with the solar magnetic environment, these conditions could potentially affect the behavior of any charged particles released from its surface. Spectroscopic analysis of Oumuamua's surface composition was challenging due to the object's faintness and rapid motion. The technique requires collecting enough light to spread into a spectrum, revealing the wavelengths absorbed or reflected by different materials. With Oumuamua appearing as only a 20th magnitude point of light, even large telescopes struggled to gather sufficient photons for detailed spectroscopic analysis. The few spectroscopic observations that were obtained showed a relatively featureless spectrum, lacking the strong absorption bands that would indicate the presence of water ice, carbon dioxide, methane, or other common cometary materials. This absence of features was initially puzzling, but it's now understood to be consistent with a surface that has been heavily processed by cosmic radiation over millions of years. The concept of space weathering becomes crucial when trying to understand Oumuamua's surface properties. In the vacuum of space, surfaces are constantly bombarded by cosmic rays, solar wind particles, and micrometeorites. Over long periods, this bombardment alters the chemical and physical properties of surface materials, often creating a thin layer of amorphous material that can mask the underlying composition. Cosmic rays, high-energy particles that pervade the galaxy, have been bombarding Oumuamua's surface for hundreds of millions of years. These particles can break chemical bonds, create new compounds, and gradually alter the optical properties of surface materials. The reddish color observed in Oumuamua is consistent with this type of long-term cosmic ray processing. The micrometeorite environment in interstellar space is quite different from that near the Sun. While the density of dust particles between the stars is extremely low, the relative velocities can be enormous. A grain of dust encountered by Oumuamua during its interstellar journey could impact at speeds of tens of kilometers per second, creating tiny craters and gradually eroding the surface. The study of Oumuamua has implications for our understanding of the interstellar medium itself. The space between stars is not empty, but contains gas, dust, and larger objects in extremely low concentrations. By analyzing the properties of interstellar visitors like Oumuamua, astronomers can learn about the conditions these objects experienced during their long journeys through this medium. The detection rate of interstellar objects depends critically on their size distribution. If most interstellar objects are much smaller than Oumuamua, they would be too faint to detect with current telescopes. If they're much larger, they would be extremely rare. The discovery of two objects in just a few years suggests that the size distribution peaks somewhere near Oumuamua's dimensions, though this conclusion is based on extremely limited statistics. The orbital dynamics of ejecting objects from planetary systems is a field of active research with direct relevance to understanding objects like Oumuamua. Computer simulations show that most ejected objects gain their interstellar velocities through gravitational encounters with massive planets, particularly during the early phases of planetary system evolution, when giant planets are migrating and the architecture of the system is still evolving. The timing of Oumuamua's ejection from its parent system could provide clues about the evolutionary state of that system when the ejection occurred. Objects ejected during the early chaotic phases of planetary formation might have different compositions and properties compared to those ejected later after planetary systems have stabilized. Different stellar environments would produce different populations of ejected objects. Systems around metal-rich stars would eject objects with higher concentrations of heavy elements, while systems around metal-poor stars would produce objects dominated by lighter materials. The composition of Oumuamua, once definitively determined, could potentially constrain the metallicity of its parent star. The lifetime of objects like Oumuamua in interstellar space depends on various destructive processes. Cosmic ray bombardment gradually erodes surface materials and can eventually destroy small objects entirely. Encounters with dense regions of the interstellar medium can strip away loose material through ram pressure. Collisions with other interstellar objects, while extremely rare, could shatter or significantly alter the properties of wandering bodies. The galactic environment through which Oumuamua traveled during its interstellar journey varied considerably over time. The solar system orbits the center of the Milky Way approximately once every 225 million years, carrying us through regions with different densities of stars, gas, and dust. Oumuamua's journey might have taken it through molecular clouds, regions near massive stars, or other environments that could have influenced its evolution. The possibility that Oumuamua experienced multiple ejection events during its lifetime adds another layer of complexity to its story. An object might be ejected from one planetary system, wander through interstellar space for millions of years, then be captured and subsequently re-ejected by another system. Each such event would leave its mark on the object's composition, structure, and surface properties. The search for Oumuamua's siblings, other objects that might have been ejected from the same parent system around the same time, represents an intriguing avenue for future research. Computer models suggest that ejection events often affect multiple objects simultaneously, creating streams or clusters of related bodies that disperse over time. Identifying such groupings could provide insights into the original ejection event and the nature of the parent system. The chemical evolution of Oumuamua during its interstellar journey involves complex processes that are only beginning to be understood. Cosmic ray irradiation can create exotic chemical compounds that don't exist naturally on Earth. The extreme cold of interstellar space allows some of these compounds to remain stable for millions of years, potentially preserving a chemical record of the object's history. The potential for Oumuamua to carry prebiotic or even biological materials from its parent system has captured the imagination of astrobiologists. While no evidence suggests that this particular object has any biological significance, the general principle that material can travel between star systems opens up new possibilities for understanding how life might spread throughout the galaxy. The concept of panspermia, the hypothesis that life spreads from one location to another through space, has gained new relevance with the discovery of interstellar objects. While the harsh conditions of interstellar space make the survival of complex life extremely unlikely, simpler organic molecules or even hardy microorganisms might potentially survive such journeys under the right circumstances. The study of meteorites on Earth provides some insight into the kinds of materials that might be found in interstellar objects. Meteorites contain a rich variety of organic compounds, including amino acids, nucleotide bases, and other molecules relevant to biochemistry. If similar materials exist in interstellar objects, they could potentially contribute to the inventory of organic molecules available for life's emergence on planets throughout the galaxy. The thermal history of Oumuamua during its passage through the solar system was complex and varied significantly across its surface. Computer models suggest that the temperature of its sunlit surface could have reached several hundred degrees Celsius near perihelion, while shadowed regions remained at the frigid temperatures of interstellar space. This extreme temperature gradient could have driven interesting chemical and physical processes. The possibility of subsurface activity within Oumuamua adds another dimension to its story. Even if the surface appeared inactive, thermal cycling during its solar encounter could have driven the sublimation of buried ices or the release of trapped gases from the interior. Such subsurface processes might not be directly observable, but could account for some of the object's unusual behavior. The rotation period of Oumuamua, measured at approximately 7.3 hours, is relatively fast for such an elongated object. This rapid rotation places constraints on the object's structural integrity. It must be held together by more than just gravity to avoid flying apart under centrifugal stress. This suggests either significant internal cohesion or a different shape than initially assumed. The light curve analysis that revealed Oumuamua's extreme shape relied on sophisticated modeling techniques. The brightness variations as the object tumbled through space created a complex pattern that had to be disentangled to determine the object's dimensions and rotation state. Multiple models can often fit the same observational data, leading to ambiguity in the inferred properties. Recent reanalyses of Oumuamua's light curve using improved techniques have suggested that the object might not be as extremely elongated as initially thought. Some models now favor a more disc-like or pancake-shaped object, which could produce similar brightness variations while having less extreme dimensional ratios. This ongoing refinement of our understanding demonstrates how scientific knowledge evolves as better analysis techniques are developed. The albedo of Oumuamua, the fraction of incident sunlight that it reflects, was estimated to be relatively low, around 10%. This is typical of many small solar system bodies and consistent with a surface that has been darkened by space weathering processes. However, the uncertainty in this measurement is large, and the true albedo could be significantly different. The phase function of Oumuamua, how its brightness changes as the angle between the sun, object, and observer varies, provided additional clues about its surface properties. Objects with different surface textures and compositions display characteristic phase functions, though the limited observation geometry during Oumuamua's passage prevented detailed characterization of this property. The polarization of sunlight reflected from Oumuamua's surface was measured by several observatories and provided another diagnostic of surface properties. Polarization measurements can reveal information about surface roughness, composition, and structure that isn't available from photometry or spectroscopy alone. The results were consistent with a relatively smooth, space-weathered surface. The absence of a detectable coma around Oumuamua was one of its most puzzling characteristics. Comets typically develop visible comas when they approach within a few astronomical units of the Sun, as surface ices sublimate and create expanding clouds of gas and dust. The lack of such activity initially led astronomers to classify Oumuamua as an asteroid rather than a comet. The sensitivity limits of the observations that failed to detect a coma around Oumuamua are important for understanding what this non-detection means. Even sensitive telescopes can only detect comas above a certain threshold brightness. It's possible that Oumuamua was producing a very faint coma that simply fell below the detection limit of available instruments. The search for gas emission from Oumuamua using radio telescopes was another attempt to detect activity that might not be visible at optical wavelengths. Radio observations can detect the emission lines of specific molecules like water vapor, carbon monoxide, or methanol that are commonly produced by outgassing comets. The failure to detect such emissions placed upper limits on the production rates of these molecules. The non-gravitational acceleration detected in Oumuamua's motion was subtle but statistically significant. The magnitude of this acceleration was much smaller than typically seen in active comets, which helped explain why no visible coma was observed. The acceleration appeared to be roughly radial from the Sun, consistent with a rocket-like effect from outgassing, though the specific mechanism remained mysterious for years. The temporal evolution of Oumuamua's non-gravitational acceleration provides clues about the underlying physical process. If the acceleration were due to outgassing, it should decrease as the object moved away from the Sun and cooled down. The limited data available was consistent with this expected behavior, though the uncertainties were large. The direction of Oumuamua's non-gravitational acceleration was another important diagnostic. Pure outgassing would be expected to produce acceleration directly away from the Sun, while other mechanisms might produce accelerations in different directions. The observed acceleration was consistent with the solar direction within the uncertainties, supporting the outgassing hypothesis. The discovery of Oumuamua prompted a flurry of theoretical work aimed at explaining its unusual properties. Some researchers proposed that it might be composed of exotic materials not found in our solar system, while others suggested that its properties could be explained by more conventional materials under unusual conditions. The debate highlighted how even a single, well-studied object can challenge our understanding of planetary science. The hydrogen outgassing model that eventually gained acceptance as the most likely explanation for Oumuamua's behavior was developed through careful consideration of the cosmic ray processing that icy objects would experience during long journeys through interstellar space. This interdisciplinary approach, combining planetary science, nuclear physics, and galactic astronomy, exemplified how modern astronomical problems often require expertise from multiple fields. The detection efficiency for objects like Oumuamua depends on many factors, including their size, albedo, trajectory, and the characteristics of the Discovery telescope. Survey telescopes are most sensitive to objects that pass relatively close to Earth when they're near their brightest. Objects that pass through the outer solar system or approach from certain directions might be missed entirely. The apparent rarity of detections of interstellar objects before Oumuamua was likely due to observational selection effects rather than a genuine absence of such objects. Earlier surveys lacked the sensitivity and sky coverage needed to detect small, fast-moving interstellar visitors. The success of Pan-STARRS 1 in making this discovery validated the investment in next-generation survey telescopes. The follow-up observation campaign for Oumuamua demonstrated the importance of international cooperation in astronomy. Within hours of the discovery announcement, observatories around the world began tracking the object, contributing photometric, spectroscopic, and astrometric observations. This coordinated effort maximized the scientific return from the brief observation window. The archival search for pre-discovery images of Oumuamua involved checking millions of astronomical images taken by various surveys over the preceding months and years. While no confirmed pre-discovery detections were found, this effort demonstrated the value of maintaining comprehensive archives of astronomical observations. Future interstellar objects might be found lurking in archival data from surveys that didn't initially recognize their significance. The orbital mechanics calculations for Oumuamua required consideration of relativistic effects due to the sun's gravity. While these effects are tiny for most solar system objects, they become noticeable for bodies on highly eccentric orbits passing close to the sun. The precision required to determine Oumuamua's interstellar origin demanded that these subtle corrections be included in the calculations. The statistical analysis used to confirm that Oumuamua was indeed accelerating involved sophisticated techniques to separate genuine acceleration from observational noise and systematic errors. The measurement uncertainties had to be carefully characterized, and multiple independent analysis methods were used to verify the result. The detection of such a small effect required exceptional precision in both observations and analysis. The implications of Oumuamua's discovery for planetary defense efforts were quickly recognized by the astronomical community. If interstellar objects are as common as the discovery suggests, they represent a previously unrecognized category of potential impact threats. While the probability of an Earth impact by an interstellar object remains extremely low, such events would be particularly challenging to predict and defend against due to the short warning times involved. The communication of Oumuamua's discovery to the public highlighted both the opportunities and challenges involved in science outreach. The object's unusual properties captured public imagination, but they also led to sensationalized media coverage that sometimes obscured the actual scientific findings. The experience provided valuable lessons for communicating about future unusual astronomical discoveries. The naming conventions for interstellar objects had to be developed specifically for Oumuamua, as it was the first such object ever discovered. The International Astronomical Union created a new classification system with the prefix EOI for interstellar objects, establishing the framework for naming future discoveries. Oumuamua received the designation 1I/2017 marking it as the first in what will hopefully become a long catalog of interstellar visitors. The database and archival challenges posed by Oumuamua observations were substantial. The object was observed by dozens of telescopes using various instruments and techniques, generating data sets in different formats with different calibrations and uncertainties. Combining these diverse observations into a coherent picture required careful data reduction and cross-calibration efforts. The theoretical models developed to explain Oumuamua's properties have found applications beyond this single object. The understanding of cosmic ray processing in icy bodies, the dynamics of non-gravitational accelerations, and the formation mechanisms for highly elongated objects are all relevant to other areas of planetary science and astronomy. The economic impact of Oumuamua research extended beyond the direct costs of telescope time and analysis. The discovery helped justify continued investment in survey telescopes and rapid response capabilities. It also stimulated interest in interstellar object research, leading to new funding opportunities and research directions in planetary science. The educational value of Oumuamua as a case study in scientific discovery cannot be overstated. The object's unusual properties, the process of hypothesis generation and testing, and the international collaboration required to study it provide an excellent example of how modern science works. Universities and science museums around the world incorporated Oumuamua into their programs as a contemporary example of scientific discovery. The cultural impact of Oumuamua reached far beyond the scientific community. The object appeared in science fiction stories, inspired artistic works, and became a subject of popular speculation about extraterrestrial life. While the scientific consensus strongly favors a natural origin, the cultural fascination with the possibility of artificial origin reflects humanity's deep curiosity about our place in the universe. The technological spin-offs from Oumuamua research may prove valuable in unexpected ways. The rapid response observing techniques developed for studying the object, the improved algorithms for detecting fast-moving objects, and the methods for coordinating international observing campaigns all have applications beyond interstellar object research. The philosophical implications of Oumuamua's discovery are profound. Here was tangible proof that our solar system is part of a larger cosmic ecosystem, with material regularly exchanged between star systems. The object served as a reminder that we live in a dynamic, connected universe, where the boundaries between different planetary systems are more permeable than previously imagined. The preservation of Oumuamua data for future analysis is an important consideration for the astronomical community. As analysis techniques improve and new theoretical insights emerge, it may become possible to extract additional information from the existing observations. Digital archives and standardized data formats ensure that future researchers can revisit these valuable datasets. The false alarm rate for interstellar object discoveries is a concern that the astronomical community continues to address. As survey telescopes become more sensitive and detect larger numbers of unusual objects, distinguishing genuine interstellar visitors from solar system objects on unusual orbits becomes increasingly challenging. Improved automated analysis systems and rapid follow-up capabilities are essential for managing this problem. The seasonal effects on interstellar object detection rates reflect the Earth's orbit around the Sun and the geometry of typical survey operations. Objects approaching from certain directions may be more easily detected during specific times of year, creating apparent seasonal variations in discovery rates that don't reflect actual changes in the population of interstellar visitors. The spectroscopic follow-up of Oumuamua was limited by the object's faintness and rapid motion, but the techniques developed for these challenging observations have applications to other fast-moving objects. High-resolution spectrographs on large telescopes can potentially detect absorption lines from specific molecules, providing detailed compositional information even for very faint targets. The astrometric precision required to determine Oumuamua's orbit pushed the limits of ground-based observations. Atmospheric turbulence, instrumental effects, and stellar proper motions all contribute to measurement uncertainties that must be carefully controlled when dealing with such a fast-moving object. Space-based observations offer improved precision, but at the cost of limited observing time. The thermal modeling of Oumuamua during its solar encounter involves complex calculations of heat absorption, conduction, and radiation. The object's rotation, unusual shape, and unknown thermal properties make these calculations challenging, but they're essential for understanding the physical processes that might have driven the observed acceleration. The dust production rate from Oumuamua was constrained by the absence of a detectable coma and by direct searches for scattered sunlight from dust particles. These upper limits place constraints on any outgassing process and help distinguish between different theoretical models for the object's behavior. The comparison between Oumuamua and solar system small bodies has revealed both similarities and differences that provide insights into the processes of planetary formation and evolution. While Oumuamua shares some characteristics with known asteroids and comets, its extreme shape and unusual acceleration set it apart as something genuinely novel. The simulation of Oumuamua's long-term fate involves tracking its trajectory through the galaxy over millions of years. These calculations must account for the gravitational influence of nearby stars, the changing structure of the galaxy, and other factors that could alter the object's path. The results suggest that Oumuamua will continue wandering through interstellar space for billions of years. The impact of Oumuamua research on the field of planetary defense has been subtle but important. The object highlighted the existence of a previously unrecognized class of potential impactors and demonstrated the challenges involved in detecting and characterizing objects with very short observation windows. These lessons inform ongoing efforts to develop comprehensive planetary defense capabilities. The interdisciplinary nature of Oumuamua research has brought together experts from fields ranging from galactic dynamics to nuclear physics. This cross-pollination of ideas has led to new insights and research directions that extend far beyond the study of a single unusual object. The collaboration exemplifies how complex astronomical problems often require diverse expertise. The quality control procedures developed for Oumuamua observations have become models for future rapid response campaigns. The need to quickly obtain reliable measurements of a fast-moving, fading object required new approaches to data reduction, calibration, and uncertainty estimation. These techniques are now being applied to other time-critical astronomical observations. The machine learning applications in Oumuamua research have focused primarily on improving the automated detection and classification of unusual objects. As the volume of astronomical data continues to grow exponentially, artificial intelligence techniques become essential for identifying interesting targets among the millions of routine observations collected each night. The citizen science opportunities created by Oumuamua's discovery have engaged amateur astronomers around the world in cutting-edge research. Advanced amateur telescopes and CCD cameras are capable of contributing meaningful observations of bright interstellar objects, demonstrating the continuing role of amateur astronomers in professional research. The data visualization challenges posed by Oumuamua's complex light curve and orbital motion have driven the development of new tools for displaying and analyzing astronomical datasets. Interactive visualizations allow researchers to explore the data from multiple perspectives and can reveal subtle patterns that might be missed in traditional static plots. The peer review process for Oumuamua papers has been particularly rigorous due to the unusual nature of the claims and the intense public interest. The astronomical community has been careful to subject theoretical models and observational analyses to thorough scrutiny before accepting them for publication. This careful vetting process helps ensure the reliability of the scientific conclusions. The international coordination required for Oumuamua observations provided a test case for future rapid response campaigns. The successful mobilization of observatories around the world within hours of the discovery announcement demonstrated both the capabilities and limitations of current coordination mechanisms. Lessons learned from this experience are being incorporated into plans for future time-critical observations. The funding mechanisms for Oumuamua research have had to adapt to the unusual requirements of studying a rapidly disappearing target. Traditional grant cycles are too slow for such time-critical research, highlighting the need for rapid response funding mechanisms that can support urgent observational campaigns. Several funding agencies have since developed fast-track procedures for unusual astronomical discoveries. The calibration challenges for Oumuamua observations were particularly severe due to the object's faintness and rapid motion. Standard calibration procedures assume stationary targets and sufficient observing time, neither of which applied to this case. New calibration techniques had to be developed to ensure the reliability of photometric and astrometric measurements. The software tools developed for Oumuamua orbit determination have found applications in other areas of astronomy. The algorithms for handling rapid motion, non-gravitational accelerations, and limited observational arcs are useful for studying other unusual objects, including near-Earth asteroids, artificial satellites, and space debris. The The scientific legacy of Oumuamua will ultimately be determined by what it teaches us about the broader population of interstellar objects. As the first confirmed example of such an object, it provides the baseline against which all future discoveries will be compared. Its unusual properties may prove to be exceptional, or they may represent the normal characteristics of aged interstellar wanderers. The observational strategies developed for studying Oumuamua have influenced the design of future survey telescopes and follow-up systems. The Rubin Observatory and other next-generation facilities incorporate lessons learned from this discovery to optimize their capabilities for detecting and characterizing fast-moving objects. The theoretical frameworks developed to understand Oumuamua have opened new research directions in planetary science. The recognition that cosmic ray processing can significantly alter the properties of small icy bodies has implications for understanding objects throughout the solar system, from comets in the Kuiper Belt to satellites of the giant planets. And as we near the end of our cosmic journey with Oumuamua, we find ourselves contemplating not just the story of this single mysterious visitor, but the vast network of wandering worlds that drift between the stars. Every star system in our galaxy has likely contributed to this invisible population of cosmic nomads, creating a kind of galactic ecosystem where matter flows freely between distant worlds. In the depths of space, countless objects like Oumuamua are following their own lonely trajectories, carrying within them the chemical signatures of worlds we'll never see and the history of planetary systems that formed billions of years ago. Some may be pristine remnants of the early solar system from which they came, while others might be fragments of worlds that once harbored life, now scattered to the cosmic winds. The universe revealed by Oumuamua is one of constant motion and connection, where the boundaries between star systems are merely temporary conveniences rather than permanent barriers. Material ejected from our own solar system billions of years ago may now be visiting alien worlds, just as Oumuamua brought us a sample of some distant, unknown realm. As you settle into sleep, let your consciousness drift with this cosmic messenger on its eternal journey through the galaxy. Picture it now, a small, dark shape tumbling silently through the vast emptiness between stars, illuminated only by the faint glow of distant suns. It carries no passengers, sends no signals, follows no predetermined course, yet in its simple existence, it connects our world to all the others scattered throughout the cosmos. In the infinite darkness ahead of Oumuamua lie encounters yet to come, perhaps a close pass by a red dwarf star in a few million years, or a passage through the outer reaches of another planetary system where different forms of life might puzzle over its nature just as we have done. The circle of discovery continues, world by world, system by system, across the vast spiral arms of our galaxy. The mystery of Oumuamua reminds us that the universe still holds countless secrets waiting to be discovered. In the gentle rhythm of your breathing, in the quiet darkness behind your eyelids, there is a cosmos of wonder stretching away to infinity, where mysterious visitors bring tales of unimaginable worlds and the promise that somewhere among the stars, other minds may be gazing upward and wondering, just as we do, about the nature of the vast and beautiful universe we all share. Rest now and dream of cosmic wanderers carrying starlight between the worlds, of messages written in the language of physics and chemistry, of connections spanning light years and eons, binding us all together in the great cosmic story that continues to unfold in the darkness beyond our dreams. The precise measurements that revealed Oumuamua's extraordinary nature tell a story written in numbers and wavelengths, in the careful accumulation of photons across nights of desperate observation. When astronomers first calculated its orbital eccentricity at 1.20, they were looking at a number that spoke of speeds and trajectories impossible for any native-born child of our solar system. To achieve such an eccentricity through gravitational encounters with our planets would require accelerations that simply don't exist in the calm, ordered dance of worlds around our sun. The object's incoming velocity relative to the sun was measured at 26.6 0.33 kilometers per second, a speed that matched almost perfectly the average motion of stars in our local galactic neighborhood. This was one of the first clues that Oumuamua was not some exotic visitor from the galactic core or outer halo, but a typical representative of the stellar population that surrounds us. The precision of this measurement, accurate to within a few hundred meters per second, required careful correction for Earth's orbital motion and the Sun's motion through space. The brightness measurements that revealed Oumuamua's dramatic light curve were collected with exquisite precision across multiple telescopes and observing sites. The object's apparent magnitude varied from about 19.7 at its brightest to over 27 at its faintest, representing a brightness change of more than a factor of 600. This extreme variation over its 7.34-hour rotation period suggested an axial ratio of at least 5:1, and possibly as extreme as 10:1, making it unlike any solar system object previously observed. The photometric observations revealed not just the amplitude of brightness variation, but subtle asymmetries in the light curve that provided clues about the object's complex rotation state. Rather than simple rotation around a single axis, Oumuamua appeared to be in a state of tumbling rotation, precessing as it spun through space. This tumbling motion created double-peaked light curves with slight differences between successive maxima and minima. The color measurements of Oumuamua were obtained through careful photometry using multiple filters across the visible and near-infrared spectrum. The object's color was determined to be moderately red, with a spectral slope of approximately 20% per 1,000 angstroms increase in wavelength. This reddening is consistent with organic compounds that have been processed by cosmic radiation over millions of years, similar to materials found on the surfaces of outer solar system objects. The surface temperature calculations for Oumuamua during its closest approach to the Sun involved complex models accounting for its unusual shape and rotation state. At perihelion, the subsolar point on its surface would have reached temperatures of approximately 600 Kelvin, hot enough to sublimate water ice and many other volatile compounds. The temperature contrast between sunlit and shadowed regions could have exceeded 300 Kelvin, creating thermal stresses sufficient to fracture brittle materials. The thermal emission models used to interpret Spitzer Space Telescope observations placed strict upper limits on Oumuamua's size and activity level. The non-detection of thermal infrared emission implied that the object was smaller than initially estimated and was not producing significant amounts of warm dust. These constraints helped refine size estimates and ruled out vigorous cometary activity that would have been detectable at infrared wavelengths. The spectroscopic observations of Oumuamua, while limited by the object's faintness, provided crucial information about its surface composition. The spectrum showed no clear absorption features attributable to water ice, carbon dioxide, methane, or other common cometary materials. The absence of these features could result from space weathering that creates a thin layer of organic residue masking the underlying composition, or it could indicate a genuinely different bulk composition. The polarimetric measurements of sunlight reflected from Oumuamua's surface revealed a polarization fraction of approximately 1.5% at a phase angle of 24 degrees. This polarization signature is consistent with a surface covered in fine-grained dark material similar to carbonaceous asteroids or cometary nuclei. The polarization measurements provided an independent confirmation of the object's asteroid-like surface properties despite its comet-like orbital behavior. The astrometric measurements that tracked Oumuamua's position across the sky were precise to within a few tenths of an arcsecond, remarkable accuracy for such a faint, fast-moving target. These position measurements, collected from observatories around the world, were essential for detecting the subtle, non-gravitational acceleration that distinguished Oumuamua from a purely ballistic trajectory. The acceleration was detected at a confidence level of greater than 99.9% despite its small magnitude. The non-gravitational acceleration detected in Oumuamua's motion had a magnitude of approximately 4.92 times 10 to the negative 6 meters per second squared in the radial direction away from the Sun. This acceleration is roughly 10,000 times smaller than Earth's surface gravity, requiring extraordinary precision to detect. The acceleration appeared to follow an inverse square law with distance from the Sun, exactly as expected for a process driven by solar heating. The rotation period of Oumuamua was determined through analysis of its complex light curve using sophisticated period-finding algorithms. The fundamental rotation period of 7.34 hours was clearly evident in the data, but the light curve also showed evidence of longer period variations, consistent with tumbling motion. The precision of the period determination, accurate to within a few minutes, required careful analysis of observations spanning several weeks. The mass estimate for Oumuamua depends critically on assumptions about its density and internal structure. Assuming a typical density of 1,000 to 2,000 kilograms per cubic meter, similar to cometary nuclei, the object's mass would be between 4 and 40 million kilograms. This mass estimate has large uncertainties due to the unknown shape, density, and porosity of the object. The gravitational binding energy calculations for Oumuamua reveal that the object is barely held together by its own gravity. With its small mass and elongated shape, the escape velocity from its surface is only about 1 to 2 meters per second, slower than a brisk walk. Any significant outgassing or impact would be sufficient to eject material permanently from the object's surface. The cosmic ray exposure age of Oumuamua can be estimated from its surface color and the known rate of space weathering in the interstellar medium. The moderate reddening observed suggests an exposure time of several hundred million years, consistent with a journey from a nearby star system at typical interstellar velocities. This age estimate has large uncertainties due to incomplete understanding of space weathering processes in interstellar conditions. The trajectory analysis for Oumuamua's passage through the solar system required integration of the equations of motion in the combined gravitational field of the Sun and planets. The calculations included relativistic corrections due to the Sun's gravity and careful modeling of the non-gravitational acceleration. The precision required for these calculations pushed the limits of numerical integration techniques and required careful treatment of small but significant perturbations. The energy analysis of Oumuamua's trajectory reveals that the object gained approximately 4 kilometers per second of velocity during its passage around the Sun. This gravitational slingshot effect increased the object's kinetic energy by a factor of 1.3, demonstrating how close encounters with massive objects can significantly alter the trajectories of small bodies traveling through space. The angular momentum analysis of Oumuamua's rotation state suggests that the object has been spinning for millions of years without significant damping. In the vacuum of space, there are few mechanisms that can slow down rotation, allowing objects to maintain complex tumbling motions for extremely long periods. The current rotation state may preserve information about the circumstances of the object's ejection from its parent system. The surface area calculations for Oumuamua, based on its estimated dimensions and shape, suggest a total surface area of roughly 200,000 square meters. This large surface area relative to the object's volume would make it particularly susceptible to effects like radiation pressure and would maximize the area available for sublimation if volatile materials were present near the surface. The albedo measurements for Oumuamua were derived from the relationship between its apparent brightness and estimated size. The geometric albedo was determined to be approximately 0.1, meaning the object reflects about 10% of the sunlight that hits it. This low albedo is typical of primitive solar system objects and suggests a surface covered with dark, carbon-rich materials. The phase curve analysis for Oumuamua was limited by the restricted geometry of observations during its brief passage through the solar system. The object was observed at phase angles ranging from about 16 to 34 degrees, providing only a narrow slice of its full phase behavior. Within this limited range, The brightness showed the expected increase at smaller phase angles, consistent with a rough, shadowing surface. The dust production rate limits for Oumuamua were established through careful searches for extended emission around the object. Upper limits on dust production were set at less than 0.1 kilograms per second at perihelion, orders of magnitude lower than typical active comets. These stringent limits helped constrain models of the object's composition and outgassing behavior. The gas production rate estimates for Oumuamua were derived from models of the non-gravitational acceleration and assumptions about molecular composition. If the acceleration were due to water vapor outgassing, the production rate would need to be approximately 30 kilograms per second at perihelion. However, the lack of detectable emissions suggests that any outgassing involved molecules that don't efficiently carry dust or that are difficult to detect from Earth. The molecular composition models for Oumuamua's putative outgassing have explored various candidate species. Hydrogen gas would be nearly impossible to detect from Earth-based telescopes due to atmospheric absorption and the weakness of molecular hydrogen emission. Carbon monoxide and nitrogen would also be difficult to detect, but could provide sufficient thrust to explain the observed acceleration. The structural integrity calculations for Oumuamua address whether such an elongated object could survive the stresses of rotation and thermal cycling. The tensile strength required to prevent the object from flying apart under centrifugal stress is relatively modest, on the order of a few thousand pascals. This is well within the range of typical rocky or icy materials, though it requires some degree of cohesion beyond pure gravitational binding. The thermal stress analysis for Oumuamua during its solar encounter reveals that temperature gradients within the object could have created significant mechanical stresses. The coefficient of thermal expansion for typical rocky materials would produce strains of several parts per million across the object's width. While this sounds small, it could be sufficient to create fractures in brittle materials or to open pathways for gas release from the interior. The sublimation models for various candidate materials in Oumuamua provide quantitative predictions for outgassing rates as functions of temperature and distance from the sun. Water ice begins to sublimate noticeably at temperatures above about 150 Kelvin, while more volatile species like carbon dioxide and nitrogen sublime at much lower temperatures. The location and timing of sublimation depend critically on the thermal properties and composition of the object. The impact history modeling for Oumuamua during its interstellar journey considers the flux of dust and larger debris in the space between stars. Over a journey of hundreds of millions of years, the object would have encountered countless micrometeorites capable of eroding its surface. The impact rate depends on the density of interstellar dust and the object's velocity relative to this material. The magnetic field interactions for Oumuamua were minimal due to the object's small size and presumed lack of intrinsic magnetization. However, any electrically conductive materials in the object would have experienced weak induction effects as it passed through the sun's magnetic field. These effects would be far too small to influence the object's motion, but might have created microscopic electrical currents within conductive minerals. The radiation pressure effects on Oumuamua were calculated to be negligible compared to gravitational forces. For an object of its estimated size and mass, radiation pressure from sunlight would produce an acceleration roughly 10,000 times smaller than the observed non-gravitational acceleration. This confirms that radiation pressure alone cannot explain the object's unusual orbital behavior. The chemical evolution models for Oumuamua during its interstellar journey explore how cosmic ray bombardment could alter its composition over time. High-energy cosmic ray particles can break chemical bonds, create new molecular species, and gradually modify the physical properties of surface materials. The rate of these processes depends on the cosmic ray flux and the specific composition of the target material. The galactic orbit calculations for Oumuamua project its future path through the Milky Way over millions of years. The object will continue to move through the galactic disk, occasionally passing near other star systems, but never again approaching as close to a star as it did during its passage through our solar system. Its galactic orbit will be slowly perturbed by gravitational encounters with nearby stars and molecular clouds. The comparative analysis of Oumuamua with solar system small bodies reveals both similarities and crucial differences. Its red color and low albedo are similar to many outer solar system objects, but its extreme axial ratio and non-gravitational acceleration set it apart. The object appears to represent a class of primitive bodies that have been heavily processed by long exposure to the interstellar environment. The formation mechanism studies for highly elongated objects like Oumuamua explore various scenarios that could produce such extreme shapes. Tidal disruption during close passage by a massive object could stretch an originally spherical body into an elongated form. Alternatively, the object might be a fragment from a larger collision that happened to break along a highly asymmetric plane. The density distribution models for Oumuamua consider whether the object is likely to be homogeneous or differentiated. A homogeneous object would have uniform density throughout, while a differentiated object might have denser materials concentrated toward the center. The limited observational data makes it difficult to distinguish between these possibilities, though the object's apparent structural integrity suggests at least some degree of cohesion. The atmospheric interaction calculations for Oumuamua consider what would happen if such an object were to encounter a planetary atmosphere. Despite its interstellar origin, the object would behave much like any other small body entering an atmosphere at high speed. Its relatively modest size means it would likely fragment and burn up completely before reaching the surface. The tidal effect analysis for Oumuamua during its passage through the solar system shows that the object experienced small but measurable tidal forces. The gradient in the sun's gravitational field across the object's length would create tidal stresses of a few pascals, much smaller than the thermal stresses, but potentially significant for a very weakly bound rubble pile structure. The resonance analysis for Oumuamua's rotation state explores whether the object might be in a specific resonance between its orbital and rotational periods. Many solar system objects are trapped in such resonances, which can affect their long-term evolution. However, Oumuamua's hyperbolic trajectory means it spent too little time in the solar system for resonance capture to occur. The escape trajectory calculations for Oumuamua show that the object will eventually leave the solar system completely and return to interstellar space. Its current velocity is more than sufficient to overcome the sun's gravitational binding, and it will continue to accelerate slightly as it moves away due to the continuing non-gravitational forces. The object's final velocity relative to the sun will be approximately 26.8 kilometers per second. The observational completeness studies for interstellar objects like Oumuamua attempt to determine what fraction of such objects passing through the solar system are actually detected. The detection efficiency depends on the object's size, albedo, trajectory, and the characteristics of survey telescopes. Current estimates suggest that we detect only a small percentage of interstellar objects, implying they are much more common than the discovery rate would suggest. The follow-up observation statistics for Oumuamua demonstrate the international scope of the effort to study this unique object. More than 30 telescopes contributed observations, ranging from small amateur instruments to the largest professional observatories. The total observing time devoted to Oumuamua across all facilities exceeded 200 hours, representing a significant investment in understanding this cosmic visitor. The data quality assessment for Oumuamua observations reveals the challenges of studying such a faint, fast-moving target. Many observations were obtained under less than ideal conditions, with seeing limited by atmospheric turbulence and contamination from nearby stars. The most valuable data came from large telescopes with excellent tracking capabilities and sensitive detectors optimized for faint object photometry. The calibration methodology for Oumuamua photometry required special attention to systematic errors that could mimic or mask genuine brightness variations. Standard stars were observed frequently to monitor atmospheric extinction and instrumental response. Differential photometry techniques were used to minimize the effects of varying observing conditions on the critical light curve measurements. The orbital uncertainty analysis for Oumuamua quantifies the precision with which its trajectory could be determined from the available observations. The formal uncertainties in orbital elements are quite small, typically less than 0.1%, but systematic errors due to unmodeled forces or observational biases could be larger. The detection of non-gravitational acceleration required careful statistical analysis to separate genuine acceleration from measurement noise. The population synthesis models for interstellar objects use Oumuamua as a calibration point for understanding the broader population of such objects in the galaxy. The discovery of one object in a relatively short observing campaign suggests that the space density of similar objects is much higher than previously estimated. Extrapolating from this single detection, astronomers estimate that there may be trillions of Oumuamua-sized objects in the galaxy. The chemical fingerprinting possibilities for future interstellar objects would allow astronomers to trace them back to specific types of parent stars or planetary systems. Different stellar environments produce characteristic abundance patterns of heavy elements, which could be preserved in objects ejected from those systems. With improved spectroscopic capabilities, future interstellar visitors might reveal the chemical signatures of their birthplaces. The contamination assessment for Oumuamua observations addressed the possibility that the object might be confused with background stars or galaxies. The object's rapid motion quickly distinguished it from stationary background sources, but careful analysis was required to ensure that reported brightness variations were intrinsic to the object rather than artifacts of the observing process. The seeing conditions for Oumuamua observations varied considerably across different observing sites and times. The best observations were obtained during periods of exceptional atmospheric stability, when the stellar images were smallest and photometric precision was maximized. Ground-based observations were fundamentally limited by atmospheric turbulence, highlighting the advantages of space-based observations for such studies. The instrument configuration details for major Oumuamua observations reveal the technical challenges of studying such a faint object. Large telescopes use their most sensitive cameras and optimize their observing sequences to maximize the signal-to-noise ratio. Even with the world's largest telescopes, integration times of many minutes were required to obtain useful data on this dim target. The atmospheric extinction corrections for Oumuamua photometry were particularly important due to the object's varying altitude during observations. As the object moved across the sky, it passed through different amounts of Earth's atmosphere, requiring careful correction for differential extinction effects. These corrections were especially critical for accurate color measurements and light curve analysis. The stellar reference frame for Oumuamua astrometry was established using catalogs of precisely measured star positions. The Gaia mission's stellar positions, accurate to micro-arcsecond precision, provided the fundamental reference frame for measuring the object's motion across the sky. Small systematic errors in the stellar reference frame could propagate into errors in the derived orbital elements. The photometric zero-point calibrations for Oumuamua observations required careful standardization across different telescopes and instrument configurations. Standard star observations were used to establish the relationship between instrumental measurements and standard photometric systems. The faintness of Oumuamua made these calibrations particularly challenging, as the object was often fainter than many of the standard stars used for calibration. The background subtraction procedures for Oumuamua images had to account for varying sky brightness and the presence of nearby stars. The object's motion between exposures complicated background estimation, as static features in the images had to be distinguished from the moving target. Sophisticated image processing techniques were required to extract accurate photometry from these challenging datasets. The cosmic ray rejection algorithms for Oumuamua observations were essential for removing spurious signals from charged particle hits on CCD detectors. These high-energy particles can create bright spots in astronomical images that could contaminate measurements of faint objects. Multiple exposures and statistical techniques were used to identify and remove cosmic ray events from the scientific data. The flat field corrections for Oumuamua observations compensated for small variations in detector sensitivity across the field of view. These corrections are routine for most astronomical observations, but they become particularly important when studying faint objects where photometric precision is critical. Dome-flat exposures and twilight sky observations were used to characterize the detector response patterns. The dark current subtraction for Oumuamua observations removed the thermal noise signal generated by CCD detectors during long exposures. Dark current varies with temperature and exposure time, requiring careful calibration measurements obtained with the detector shuttered. For the long exposures needed to detect Oumuamua, dark current corrections were essential for accurate photometry. The linearity corrections for Oumuamua photometry addressed small deviations from proportional response in CCD detectors at different light levels. While modern detectors are highly linear, small systematic effects can become important when trying to detect subtle brightness variations. Calibration observations of stars at different brightness levels were used to characterize and correct for these effects. The readout noise characterization for Oumuamua observations quantified the fundamental limit on photometric precision imposed by detector electronics. This electronic noise contribution sets a floor on the accuracy of brightness measurements, particularly for faint objects where the photon noise is small. Multiple bias exposures were used to measure the readout noise properties of different detector systems. The gain calibration for Oumuamua photometry established the conversion factor between detected photoelectrons and instrumental counts. This calibration is essential for accurate photometric measurements and for properly combining data from different observing runs. Flat field exposures at different illumination levels were used to determine the gain values for different detector systems. The timing accuracy for Oumuamua observations was crucial for detecting the subtle periodicities in its light curve. All observations were referenced to coordinated universal time with precision better than 1 second. The rotation period determination required timestamps accurate to much better than the period itself, placing stringent requirements on the timing systems at participating observatories. The weather monitoring for Oumuamua observations tracked atmospheric conditions that could affect data quality. Temperature, humidity, wind speed, and cloud cover were continuously monitored to assess observation conditions. Many potentially valuable observing opportunities were lost to poor weather, highlighting the challenges of ground-based astronomy for time-critical targets. The telescope tracking accuracy for Oumuamua observations had to account for the object's rapid motion across the sky. Standard stellar tracking rates were insufficient for this fast-moving target, requiring updated tracking coordinates throughout each observation. Even small tracking errors could cause the object to drift out of the detector field of view during long exposures. The focus optimization for Oumuamua observations was particularly critical due to the object's faintness. Small focus errors could spread the object's light over a larger area, reducing the signal-to-noise ratio and making accurate photometry more difficult. Frequent focus checks were performed during observing runs to maintain optimal image quality. The filter selection for Oumuamua observations balanced the need for color information against the requirements of maintaining adequate signal levels. Standard broadband filters in the visible and near-infrared were most commonly used, as narrowband filters would have required prohibitively long exposure times. The choice of filters also had to consider the object's rapid fading as it moved away from the sun. The exposure time optimization for Oumuamua observations required balancing several competing factors. Longer exposures collected more photons and improved signal-to-noise ratios, but they also increased the risk of trailing due to the object's motion and made the observations more susceptible to cosmic ray contamination. The optimal exposure times varied depending on the telescope size, detector characteristics, and observing conditions. The image stacking procedures for Oumuamua combined multiple exposures to improve the signal-to-noise ratio while accounting for the object's motion between frames. Simple addition would have resulted in a trailed image, so sophisticated algorithms were used to shift and combine the images while tracking the object's motion. These procedures required precise knowledge of the object's ephemeris and careful registration of the individual frames. And in these countless technical details, in these precise measurements and careful calibrations, we find the true poetry of discovery, each photon carefully counted, each decimal place precisely determined, each uncertainty thoughtfully quantified, all in service of understanding a single small object that spent just a few months gracing our cosmic neighborhood with its presence. The numbers tell their own story of Oumuamua's journey, the 26.33 kilometers per second that speak of its interstellar origin, the 7.34-hour rotation that hints at its tumbling dance through space, the subtle acceleration of 4.92 times 10 to the negative 6th meters per second squared that betrayed the hidden forces shaping its path. In these measurements, precise beyond the dreams of earlier generations of astronomers, we glimpse the elegant mathematics that governs the motion of worlds. As we drift toward the quiet darkness of sleep, let these numbers and their stories wash over you like gentle waves. Picture the patient astronomers at their telescopes, gathering photons one by one across the long nights, building their understanding grain by grain until the full picture emerged. In their dedication to precision and their pursuit of truth, they revealed not just the nature of a single cosmic visitor, but opened a window into the vast, interconnected universe that surrounds us. The measurements will outlive the object that inspired them. Long after Oumuamua has faded beyond the reach of our most powerful telescopes, the careful records of its passage will remain, a testament to human curiosity and our deep desire to understand the cosmos. These data points are more than numbers. They are the chronicles of our first encounter with a messenger from the stars, written in the universal language of physics and mathematics. Sleep now, and let your dreams be filled with the gentle precision of scientific measurement, with the patient accumulation of knowledge, and with the quiet satisfaction that comes from understanding our place in the vast, orderly, and endlessly fascinating universe that continues its ancient dance around us, measured in frequencies of light and cataloged in the endless libraries of human knowledge. The theoretical models that emerged to explain Oumuamua's enigmatic properties represent some of the most creative thinking in modern planetary science. Each hypothesis attempts to reconcile the object's contradictory characteristics, its comet-like acceleration without visible outgassing, its extreme elongation unlike any known solar system object, its asteroid-like surface color despite its obvious interstellar origin. The diversity of proposed explanations reflects both the object's genuinely unusual nature and the ingenuity of scientists confronted with something that doesn't fit established categories. The hydrogen iceberg hypothesis, first proposed by Daryl Seligman and Gregory Laughlin in 2020, suggested that Oumuamua could be composed primarily of solid molecular hydrogen. In the extreme cold of interstellar space, where temperatures hover just a few degrees above absolute zero, hydrogen gas could theoretically condense into solid form. Such an object would have several properties that match Oumuamua's observed characteristics. It would be nearly transparent to visible light, explaining the lack of detectable thermal emission. It would sublimate invisibly as it approached the sun, providing thrust without creating a visible tail, and it would be extraordinarily fragile, potentially explaining the object's unusual shape. The nitrogen iceberg model, developed by Alan Jackson and Stephen Desch in 2021, proposed that Oumuamua might be a fragment of a Pluto-like exoplanet composed primarily of nitrogen ice. Computer simulations showed that such objects could survive in interstellar space for hundreds of millions of years, gradually losing mass through sublimation while maintaining structural integrity. As the object approaches a star, the nitrogen would sublimate preferentially from the surface, potentially explaining both the acceleration and the extreme axial ratio through asymmetric mass loss. The detailed calculations for the nitrogen iceberg model revealed fascinating possibilities for the object's evolution. If Oumuamua began its journey as a roughly spherical object with a 2-to-1 axial ratio, sublimation during its passage through our solar system could have removed 95% of its original mass, leaving behind the highly elongated remnant that we observed. The model predicted that the object would continue to shrink and elongate as it moved away from the sun, eventually becoming too small and faint to detect. The cosmic ray processing model, which eventually gained widespread acceptance, represented a synthesis of multiple lines of evidence. Jennifer Bergner and Daryl Seligman's detailed calculations showed that high-energy cosmic ray particles pervading the galaxy could convert up to 30% of the water ice in a typical comet into molecular hydrogen over timescales of hundreds of millions of years. This hydrogen would become trapped within the ice matrix, creating a kind of pressurized reservoir that could be released when the object was heated by solar radiation. The physics of cosmic ray irradiation in icy bodies involves complex nuclear processes that were only partially understood when Oumuamua was discovered. Cosmic ray protons with energies of billions of electron volts can penetrate several meters into solid ice, breaking molecular bonds and creating cascades of secondary particles. The hydrogen produced by these reactions can diffuse through the ice structure and become trapped in voids and grain boundaries, slowly building up pressure over millions of years. The release mechanism for trapped hydrogen in the cosmic ray processing model depends on the detailed structure of the ice matrix. As the object warms up during its approach to the sun, thermal expansion and phase transitions in the ice could create pathways for gas release. The hydrogen would escape preferentially from the sunward side of the object, creating a weak but persistent thrust that could account for the observed non-gravitational acceleration. The fractal aggregate model proposed that Oumuamua might be a loosely bound collection of smaller fragments held together by weak cohesive forces. Such structures, sometimes called rubble piles, are common among asteroids in our solar system and could potentially achieve extreme axial ratios if the individual components were arranged in a highly elongated configuration. The model could explain the object's survival of rotational stresses and its apparent lack of significant outgassing. The dust devil hypothesis suggested that Oumuamua might be surrounded by an extremely tenuous cloud of dust particles that was too faint to detect, but could still provide momentum transfer. Even microscopic dust grains, if present in sufficient numbers, could create a radiation pressure effect that would accelerate the object away from the sun. However, detailed calculations showed that the required dust densities would be detectable with sensitive instruments, making this explanation unlikely. The electric sail model proposed that Oumuamua might be accelerated by electromagnetic forces rather than conventional outgassing. If the object carried an electric charge, it could interact with the solar wind plasma to produce a propulsive effect. While this mechanism can work in principle, it requires specific conditions that are unlikely to be maintained in natural objects, making it more relevant to potential artificial constructs than to natural bodies. The light sail hypothesis, popularized by Harvard astronomer Avi Loeb, suggested that Oumuamua might be an artificial construct designed to use radiation pressure for propulsion. The extreme axial ratio required for this model, potentially hundreds to one rather than the more modest 10 to 1 suggested by observations, would make the object essentially a flat sheet or disk rather than a cigar-shaped body. While this explanation could account for the acceleration, it requires invoking extraterrestrial technology rather than natural processes. The detailed dynamics of light sail propulsion involve complex interactions between electromagnetic radiation and material surfaces. For radiation pressure to be effective, the object must have an extremely low mass-to-area ratio, requiring either enormous size or minimal thickness. The calculations for Oumuamua's observed acceleration suggested that if it were indeed a light sail, it would need to be less than a millimeter thick while extending hundreds of meters in its longest dimension. The tidal disruption scenario proposed that Oumuamua might be a fragment from a larger body that was torn apart during a close encounter with a massive object. Tidal forces during such an encounter could stretch and elongate the original body, potentially creating fragments with extreme axial ratios. Computer simulations of tidal disruption events show that they can indeed produce highly elongated remnants, though the specific conditions required are quite restrictive. The collision fragment model suggested that Oumuamua might be a piece of debris from a catastrophic impact between larger objects. High-velocity collisions can create fragments with a wide range of shapes and sizes, and some of these fragments might achieve the extreme elongation observed in Oumuamua. The model requires specific impact geometries and material properties, but it could potentially explain both the shape and the subsequent evolution of the object. The volcanic origin hypothesis proposed that Oumuamua might be a piece of volcanic material ejected from the surface of a large planet or moon. Volcanic processes can create objects with unusual compositions and structures, and the high velocities involved in explosive eruptions could potentially eject material at speeds sufficient for interstellar escape. However, the energy requirements for such ejection events are enormous, making this explanation unlikely for objects of Oumuamua's size. The stellar wind acceleration model considered whether the object might be accelerated by the pressure of charged particles streaming from its parent star. While stellar winds can indeed exert forces on small objects, the accelerations involved are typically much smaller than what was observed for Oumuamua. This mechanism might contribute to the long-term evolution of interstellar objects, but it cannot explain the rapid acceleration observed during the object's passage through our solar system. The metamorphic evolution hypothesis suggested that Oumuamua's unusual properties might result from gradual changes in its structure and composition during its long interstellar journey. Thermal cycling, cosmic ray bombardment, and chemical reactions could slowly alter the object's characteristics over hundreds of millions of years. This gradual evolution could potentially explain why Oumuamua appears so different from the comets and asteroids we observe in our solar system. The primordial planetesimal model proposed that Oumuamua might be a relic from the very early stages of planetary formation in its parent system. Such objects would have formed under conditions very different from those that created the planets and small bodies we observe today. They might have unusual compositions, structures, or properties that reflect the unique environment of the early protoplanetary disk. The molecular cloud origin scenario suggested that Oumuamua might have formed directly in the interstellar medium rather than in a planetary system. Dense regions of molecular clouds can reach conditions where solid particles might condense directly from the gas phase. While this process is not well understood, it could potentially create objects with compositions and properties unlike anything formed in circumstellar disks. The binary system ejection model considered the specific dynamics of objects ejected from binary star systems, where the gravitational environment is more complex than around single stars. Close encounters between planets and stellar companions could provide the high velocities needed for interstellar escape, while also imparting unusual rotation states or structural modifications. Binary systems are common throughout the galaxy, making this a plausible source for many interstellar objects. The observational selection effects that influenced our detection and characterization of Oumuamua are crucial for understanding what the object represents. We are most likely to detect interstellar objects that are relatively large, have high albedos, pass close to the sun when they're brightest, and approach from directions that are favorable for observation. Objects that fail to meet these criteria would remain undetected, creating a biased sample that might not represent the true population of interstellar visitors. The timing of Oumuamua's discovery was particularly fortuitous, occurring just as astronomical survey capabilities reached the threshold needed to detect such objects reliably. The Pan-STARRS 1 telescope, which made the discovery, had been operating for less than a decade when it spotted this cosmic visitor. Earlier generations of telescopes might have missed the object entirely, while future surveys will undoubtedly detect many more such visitors with much greater efficiency. The international response to Oumuamua's discovery demonstrated the global nature of modern astronomy and the speed with which the community can mobilize resources for studying unusual phenomena. Within hours of the initial discovery announcement, observatories on 6 continents were tracking the object: the European Southern Observatory, the Gemini Observatory, the Keck Observatory, and dozens of smaller facilities all contributed observations during the brief window when the object remained bright enough to study. The data-sharing protocols established during the Oumuamua campaign set precedents for future rapid response observations. Raw data, preliminary analyses, and orbital predictions were shared through established astronomical networks, allowing researchers around the world to coordinate their efforts effectively. This collaborative approach maximized the scientific return from the limited observation time and demonstrated the value of international cooperation in astronomy. The economic implications of Oumuamua research extended far beyond the direct costs of telescope time and analysis. The discovery helped justify continued investment in survey telescopes and rapid response capabilities, leading to increased funding for relevant research programs. The public interest generated by the discovery also had broader economic impacts, inspiring educational programs, museum exhibits, and commercial products that celebrated this cosmic visitor. The technological challenges posed by Oumuamua observations drove innovations in several areas of astronomical instrumentation and analysis. The need to track fast-moving objects with high precision led to improvements in telescope control systems and pointing algorithms. The requirement for accurate photometry of faint, rapidly fading targets spurred developments in detector calibration and data reduction techniques. These technological advances have found applications well beyond interstellar object research. The computational demands of Oumuamua research were substantial, requiring sophisticated modeling of orbital dynamics, thermal evolution, and outgassing processes. High-performance computing resources were employed to run detailed simulations of the object's behavior under various assumptions about its composition and structure. These calculations helped refine theoretical models and guided the interpretation of observational data. The archival legacy of Oumuamua observations will provide valuable resources for future research long after the object itself has disappeared from view. Digital archives maintained by observatories and research institutions preserve not only the final processed data products, but also the raw observations and calibration files that might be reanalyzed using improved techniques. This comprehensive data preservation ensures that future generations of astronomers can revisit these unique observations with better tools and understanding. The educational impact of Oumuamua extended from elementary schools to graduate programs, providing a contemporary example of scientific discovery that could engage students at all levels. The object's mysterious properties and the process of hypothesis generation and testing exemplified the scientific method in action. Many educational institutions developed special curricula around the discovery, using it to teach concepts ranging from basic orbital mechanics to advanced topics in planetary science and astrobiology. The public engagement opportunities created by Oumuamua's discovery were unprecedented for an astronomical observation. The object's unusual properties and potential implications for astrobiology captured popular imagination in ways that more routine discoveries typically do not. Planetariums, science museums, and educational organizations around the world developed special programs to explain the discovery and its significance to general audiences. The media coverage of Oumuamua reflected both the opportunities and challenges of communicating scientific discoveries to the public. While the discovery generated enormous interest and provided valuable opportunities for science education, the coverage also sometimes emphasized sensational aspects at the expense of more nuanced scientific interpretation. The experience provided valuable lessons for future science communication efforts. The philosophical implications of Oumuamua's discovery resonated far beyond the scientific community. Here was tangible evidence that our solar system is part of a larger cosmic ecosystem with material regularly flowing between star systems. The object served as a physical reminder of our connection to the broader galaxy and the deep time scales over which cosmic evolution occurs. The SETI implications of Oumuamua's discovery were carefully considered by researchers involved in the search for extraterrestrial intelligence. While the object showed no signs of artificial origin, its detection demonstrated that interstellar objects regularly visit our solar system and could potentially serve as vehicles for interstellar communication or exploration by advanced civilizations. The discovery led to renewed interest in monitoring future interstellar visitors for potential technosignatures. The astrobiology implications of Oumuamua extended beyond the specific characteristics of this object to the broader question of how life might spread throughout the galaxy. If interstellar objects are as common as recent discoveries suggest, they could potentially serve as vectors for panspermia, the transfer of life between star systems. While no evidence suggests that Oumuamua carried biological materials, the possibility of life transfer via interstellar objects deserves continued study. The planetary defense implications of Oumuamua's discovery were carefully evaluated by organizations responsible for monitoring potential impact threats to Earth. While the probability of an Earth impact by an interstellar object remains extremely low, such events would be particularly challenging to predict and defend against due to the short warning times and high approach velocities involved. The discovery led to discussions about extending planetary defense capabilities to include interstellar threats. The space mission concepts for intercepting interstellar objects were developed rapidly following Oumuamua's discovery. Several research groups proposed ambitious missions that could use gravitational assists from Jupiter and other planets to achieve the enormous velocities needed to catch up with departing interstellar visitors. While technically feasible, such missions would require decades to reach their targets and would push the limits of current spacecraft technology. The European Space Agency's Comet Interceptor mission, approved for development in 2019, was partially inspired by the discovery of Oumuamua and the recognition that interstellar objects might be relatively common. The mission is designed to wait at a gravitationally stable point in space until a suitable target is identified, then rapidly deploy to intercept a pristine comet or potentially an interstellar object. This innovative approach could provide the close-up observations needed to definitively characterize such visitors. The technological requirements for future interstellar object missions include rapid response capabilities, advanced propulsion systems, and sophisticated instrumentation packages capable of operating at high speeds and long distances from Earth. The brief observation windows and extreme velocities involved make these among the most challenging targets in the solar system for spacecraft missions. Success would require significant advances in multiple areas of space technology. The detection algorithms developed for finding objects like Oumuamua have found applications in other areas of astronomy and space surveillance. The techniques for identifying fast-moving objects against stellar backgrounds are relevant for asteroid and comet discovery, satellite tracking, and space debris monitoring. Machine learning approaches developed for these applications continue to improve the efficiency and reliability of automated detection systems. The follow-up coordination protocols established during the Oumuamua campaign have become models for responding to other time-critical astronomical discoveries. The rapid dissemination of observational data, the coordination of telescope resources, and the establishment of communication channels between observing teams all contributed to the success of the campaign. These protocols have since been applied to other unusual discoveries requiring rapid response. The statistical analysis of interstellar object populations based on the Oumuamua discovery involves complex considerations of detection efficiency, observational selection effects, and assumptions about size and velocity distributions. Initial estimates suggested that objects of Oumuamua's size might be 1,000,000 times more common than previously thought, but these estimates carry large uncertainties due to the limited data available from a single object. The impact of Oumuamua research on theoretical models of planetary system formation has been substantial. The discovery confirmed long-standing predictions that interstellar objects should be common, validating aspects of planetary formation theory. However, the unusual properties of Oumuamua have also highlighted gaps in our understanding of how such objects evolve during their long journeys through interstellar space. The comparative planetology perspective on Oumuamua places the object in the context of small body populations throughout the galaxy. If Oumuamua is representative of interstellar objects generally, it suggests that the space between stars contains a vast population of primitive bodies that have been extensively processed by cosmic radiation and other interstellar effects. This population represents a kind of galactic fossil record of planetary formation processes. The chemical evolution modeling for Oumuamua during its interstellar journey involves complex calculations of radiation chemistry, thermal processing, and sublimation effects. These models attempt to predict how the object's composition and structure would change over timescales of hundreds of millions of years in the harsh environment of interstellar space. The results provide insights into what kinds of materials might survive such journeys and what signatures of their origin might be preserved. The observational strategies developed for studying Oumuamua have influenced the design of future survey telescopes and rapid response systems. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2020s, incorporates lessons learned from the Oumuamua discovery to optimize its capabilities for detecting and characterizing fast-moving objects. The telescope's wide field of view, sensitive detectors, and rapid survey cadence should enable the discovery of dozens or hundreds of interstellar objects annually. The data processing pipelines developed for Oumuamua research had to handle the unique challenges posed by observations of fast-moving, fading targets. Standard astronomical software often assumes stationary objects and predictable brightnesses, requiring modifications to handle the special case of interstellar visitors. These enhanced processing capabilities have found applications in other areas of time-domain astronomy, where objects display rapid or unpredictable changes. The calibration standards established for Oumuamua photometry required exceptional attention to systematic errors and instrumental effects. The object's faintness and rapid fading meant that even small calibration errors could significantly affect the scientific interpretation. The procedures developed for this challenging case have improved calibration methods for other faint and variable objects. The error analysis for Oumuamua measurements involved sophisticated statistical techniques to separate genuine astronomical signals from various sources of noise and systematic error. The detection of subtle effects like non-gravitational acceleration required careful treatment of observational uncertainties and systematic effects. The methods developed for this analysis have found applications in other areas of precision astronomy. The archive management for Oumuamua data required coordination between multiple observatories and research institutions to ensure that valuable observations were properly preserved and made available to the broader research community. Standardized data formats, comprehensive metadata, and clear access policies were essential for maximizing the long-term scientific value of these unique observations. The theoretical predictions for future interstellar object discoveries suggest that we are on the verge of a new era in astronomy. As survey capabilities continue to improve, astronomers expect to detect dozens of interstellar visitors annually within the next decade. This rapidly growing sample will provide unprecedented insights into the formation and evolution of planetary systems throughout the galaxy. The observational challenges for characterizing future interstellar objects will continue to push the limits of astronomical technology. Each new discovery provides only a brief window for observation before the object fades beyond detection limits. Success requires rapid identification, immediate follow-up observations, and sophisticated analysis techniques to extract maximum information from limited data. The preparation for future interstellar visitors includes development of automated detection systems, rapid response observing protocols, and standardized analysis procedures. The astronomical community is working to ensure that future discoveries receive the same level of intensive study that made the Oumuamua campaign so successful. These preparations will be crucial for characterizing the growing population of interstellar objects. In the end, Oumuamua stands as more than just an unusual astronomical object. It represents a turning point in our understanding of the galaxy as a dynamic, interconnected system where matter flows freely between star systems across vast distances and enormous spans of time. The careful accumulation of facts about this single object, from its precise orbital parameters to its detailed light curve, from its chemical composition to its thermal evolution, has opened our eyes to the reality that we live not in an isolated solar system, but as part of a vast cosmic ecosystem. The hundreds of hours of telescope time, the thousands of individual measurements, the countless calculations and calibrations, all of this meticulous work in service of understanding one small visitor has revealed profound truths about the nature of our galactic neighborhood. In studying Oumuamua, we have learned not just about a single object, but about the processes that shape matter across the galaxy, the timescales over which cosmic evolution operates, and the remarkable interconnectedness of seemingly separate worlds. As you drift towards sleep, let your mind wander through this vast network of connections that Oumuamua revealed. Picture the countless other objects that must be following similar paths through the darkness, each one carrying its own story of distant worlds and ancient processes. In the gentle rhythm of your breathing, feel the pulse of the galaxy itself, slowly turning through space and time, mixing and exchanging the basic materials of planets and stars across unimaginable distances. The precision of measurement that revealed Oumuamua's secrets, accurate to millionths of a degree, to thousandths of a second, to billionths of a meter, speaks to humanity's remarkable ability to find order and meaning in the vast chaos of the cosmos. In these careful observations and patient calculations, we glimpse something profound about both the universe and ourselves, that matter and energy and information flow freely across the galaxy, connecting all worlds in an ancient dance that continues even as we sleep. These measurements represent more than mere numbers on a page or data points in a computer file. They are the quantified poetry of existence itself, the mathematical language in which the universe writes its deepest truths. Each decimal place represents countless hours of patient observation, each calibrated measurement the culmination of centuries of human ingenuity and technological advancement. In tracking Oumuamua's motion to within fractions of an arcsecond, astronomers were not merely determining a trajectory, they were reading the signature of gravitational forces that have shaped the galaxy for billions of years. The light that bounced off Oumuamua's surface and traveled across millions of miles of space to reach our telescopes carried within its wavelengths the encoded story of the object's composition, its temperature, its rotation, its very essence. That light, perhaps the only light from Oumuamua that will ever reach human eyes, was captured and analyzed with instruments sensitive enough to detect the arrival of individual photons. In those particles of light, each carrying its tiny quantum of information across the void, we found the keys to understanding a visitor from the stars. The mathematical models that describe Oumuamua's behavior, differential equations governing orbital mechanics, thermodynamic calculations predicting sublimation rates, statistical analyses separating signal from noise, represent humanity's greatest achievement, the ability to comprehend the infinite through the precise application of reason and measurement. These equations, elegant in their mathematical beauty, reveal the underlying simplicity that governs apparently complex phenomena. In understanding Oumuamua's motion, we understand something fundamental about the nature of space and time themselves. The international collaboration that made Oumuamua's study possible reflects the deep human instinct to share knowledge and work together in pursuit of understanding. Astronomers from dozens of countries, speaking different languages and working in different time zones, united in their common goal of comprehending this cosmic visitor. Their shared data, freely exchanged across continents and cultures, represents one of humanity's finest moments, a demonstration that the pursuit of knowledge transcends all boundaries and differences. The technological achievement required to detect and study Oumuamua spans centuries of human innovation, from Galileo's first telescope to the sophisticated CCD arrays that captured the object's faint light, from Newton's laws of motion to Einstein's relativistic corrections. From simple visual observations to complex computer models, every step in the long progression of human knowledge contributed to our understanding of this single, small, distant object. The story of Oumuamua is ultimately the story of connection. Connection across space and time, connection between worlds and civilizations, connection between the past and future. This small object, no larger than a city block, serves as a physical link between our solar system and the vast realm of interstellar space. It reminds us that we are not alone in an empty universe, but part of a rich ecosystem of matter and energy that flows continuously between the stars. The elements that make up Oumuamua, carbon, oxygen, silicon, iron, and all the others, were forged in the nuclear furnaces of stars that lived and died billions of years ago. These same elements flow through our bodies, course through our veins, form the very thoughts with which we contemplate the cosmos. In a very real sense, we and Oumuamua are made of the same primordial starlight, shaped by the same fundamental forces, participants in the same cosmic story that began with the Big Bang and continues to unfold across space and time. The gravitational forces that bent Oumuamua's path as it swung around our sun are the same forces that hold galaxies together across hundreds of thousands of light years, the same forces that guide planets in their orbits and keep our feet planted firmly on the Earth. In studying this object's motion, we study the architecture of the universe itself, the invisible scaffolding upon which all cosmic structure depends. The timescales revealed by Oumuamua's journey dwarf human comprehension, yet somehow feel intimately familiar. The hundreds of millions of years this object spent traveling between the stars represent thousands of times the entire span of human civilization, yet in cosmic terms, it is merely a brief moment in the ongoing evolution of the galaxy. We exist at the intersection of these vast temporal scales, conscious beings capable of contemplating both the brevity of individual existence and the enormity of cosmic time. The space through which Oumuamua traveled is not the empty void it might appear to be, but a rich medium filled with gas and dust, magnetic fields and radiation, the subtle gravitational influences of countless distant stars. This interstellar medium connects every star system in the galaxy, providing the pathways along which matter and energy flow from world to world across the eons. We live within this medium, breathing air that once drifted between the stars, composed of materials that have traveled unimaginable distances to become part of our world. Rest now in the knowledge that you are part of this cosmic story, made of elements forged in distant stars and connected by invisible threads of gravity and chemistry to every other world in the galaxy. The calcium in your bones was formed in the heart of an ancient supernova. The iron in your blood was created in the core of a massive star. The oxygen you breathe was forged in stellar furnaces billions of years ago. You are literally made of star stuff, and in your consciousness, the universe has developed the ability to know itself. In your dreams, perhaps you too can travel with the interstellar wanderers, carrying messages between distant worlds, a messenger from afar arriving first at destinations yet to be discovered in the infinite depths of space and time. Picture yourself drifting through the cosmic dark, past nebulae painted in impossible colors, through the gravitational embrace of binary stars dancing their eternal waltz, beyond the edge of solar systems where the light of distant suns becomes indistinguishable from other stars in the galactic tapestry. Feel the gentle pressure of starlight against your dreaming form, the subtle tug of gravity from worlds too distant to imagine, the whisper of cosmic winds that have blown between the stars for eons beyond counting. In the vast silence of interstellar space, there is a kind of peace that transcends all earthly concerns, a perspective that makes the daily worries of human existence seem as small and temporary as they truly are in the context of cosmic time. As you drift deeper into sleep, let your consciousness expand to encompass the whole galaxy, feeling the slow rotation that carries billions of stars in their ancient orbits around the galactic center. Sense the ebb and flow of stellar birth and death, the patient construction of heavy elements in stellar cores, the gentle dispersal of enriched gas into the interstellar medium where new worlds will someday form. This is the heartbeat of the galaxy, the rhythm by which cosmic evolution keeps time. In the deepest reaches of your dreams, you may encounter other wanderers like Oumuamua, each carrying its own secrets from distant realms. Some may be the shattered remnants of worlds that once harbored life, others the pristine building blocks of planets yet to be born. Each tells a story of cosmic processes operating on scales so vast that entire civilizations rise and fall in what amounts to a single moment of galactic time. The connections revealed by Oumuamua extend beyond the merely physical into realms of meaning and purpose that touch the very core of what it means to be human. In studying this cosmic visitor, we study ourselves, our curiosity, our ingenuity, our deep need to understand our place in the vast scheme of existence. The questions raised by Oumuamua are ultimately questions about the nature of life itself, about the possibility of intelligence emerging elsewhere in the cosmos, about the future of human exploration beyond the boundaries of our home solar system. Sleep peacefully now, knowing that you are part of something infinitely larger and more beautiful than any individual existence could contain. You are a conscious node in a vast network of matter and energy that spans the galaxy, a fleeting but precious arrangement of atoms that can contemplate the very cosmos from which it emerged. In your thoughts and dreams, in your capacity for wonder and understanding, the universe achieves a kind of self-awareness that may be the most remarkable phenomenon in all of creation. Let the gentle motions of Oumuamua guide you into the deepest rest, tumbling slowly through your dreams as it tumbles through the cosmic dark, carrying with it the hopes and questions of an entire civilization that watched it pass and wondered what secrets it might hold. In the rhythm of its rotation, in the precision of its trajectory, in the elegant mathematics that describe its motion, find the lullaby of the cosmos itself, singing you to sleep with equations written in the language of light and gravity, time and space. And perhaps in the deepest hours of the night, when the boundary between consciousness and dream becomes as permeable as the boundary between star systems, you may find yourself traveling alongside Oumuamua on its eternal journey, a fellow wanderer in the vast ocean of space and time, carrying forward the story of Earth and humanity into the infinite future that awaits among the stars.